So today we're going to learn how to read the solubility curve graph. First thing when it comes to graph is you got to look at what's on the axes. So if you look on the x-axis, which is the independent variable, this is the temperature in degrees Celsius. So we control the temperature. Independent means that I can pick which temperatures I'm going to increase the temperature to before the lab even starts. And then the y-axis is the dependent variable, which means what am I going to measure while I'm doing the lab? So the independent variable is the one that we're going to manipulate. The dependent variable is the one we're going to measure that in response to the independent variable during the lab. So you can't get the dependent variable until you actually do the lab. So let's just pick one of the curves at random. I'm going to pick KNO3. If you look at KNO3, it has the steepest slope. That means that the solubility curve increases at the greatest rate. The solubility of KNO3 changes the most with changing temperature. I'm just going to pick a random temperature so everybody finds 60 degrees Celsius on the bottom of your graph. And then you're going to run your finger up to KNO3, which is right here. If you are reading exactly on the line is going to represent a saturated solution. That means that's the exact amount that will dissolve in 100 grams of water. So here's how we write this. This is going to be a ratio. So how you're going to read this is you're going to say 110 grams of KNO3 dissolves in 100 grams of water. That's what you read off of that. That 100 grams of water is important because the more water you have, the more will dissolve. The less water you have, the less will dissolve. So both parts of these are important. So now let's look at what if I didn't have 110? What if I only had 80 grams of KNO3 dissolved in 100 grams of water? That is what would be considered an unsaturated solution. Now, there's a third part of the graph. Let's say you had 140 grams of KNO3 dissolved in 100 grams of water. This is what we would call a supersaturated solution. So on the line is saturated. That represents the solubility of KNO3 or how much will dissolve. Under the graph, under the line, would represent unsaturated. Over the line would represent supersaturated. So you might be smart enough to say, hey, you told me that saturated was the most that could dissolve. Well, here's how you make a saturated solution. What I would do is I would heat my solution to 90 degrees Celsius or something above the saturated mark. After I heat it to 90 degrees Celsius, I can easily dissolve 140 grams of KNO3 in 100 grams of water. Then I would let my solution cool. If you leave it sitting out on the table, it will cool down. Now, as long as I don't touch it, if I tap the container, a lot of the solid will precipitate out. That's what we call a solid that settles to the bottom of a solution is a precipitate. The other thing that could happen is if I drop one more crystal in there, called a seed crystal, that would also cause a large amount of solid to precipitate out. So as long as I leave a saturated, if I take a saturated solution and I cool it down, it will become a supersaturated solution as long as I don't disturb it. That's how we make a supersaturated solution. We take an unsaturated or saturated solution and we let it cool down. So there's the different parts of the graph. Each of these curves has a different part of the graph. Now let's go to another aspect of this, of what we can determine from this graph. So notice that with KNO3, as the temperature increases, the solubility also increases. So let's label some of these that as the temperature goes up, the solubility also goes up. Same thing for NaNO3. Same thing for Ki. As the solubility goes up, as the temperature goes up, the solubility also goes up. Okay, who can find a line on here that is the opposite of that? As the temperature goes up, the solubility goes down. Sam? SO2. SO2 is one of them. Anybody find a different one? Hazel? NH3 is another one. What's the last one? Cl. These are, so SO2, NH3, and HCl, the solubility is going to go down with increasing temperature. Who's got their thinking cap on today? Who can look at these sets of compounds and tell me the difference in the chemical formulas? So these are ionic bonds, and these are covalent bonds. So let's start a little list. We're going to start a list of the things that affect the solubility. So the first thing we've talked about and what the whole graph is about is temperature. Temperature is the first factor that affects the solubility. The second is bond type. Ionic compounds are all solids at room temperature. Covalent compounds like these small covalent compounds, all of these three compounds are gases at room temperature. So what that means is temperature affects the solubility of both of them. Bond type affects the solubility of both of them. The solubility of gases decreases with increasing temperature. The solubility of solids increases with increasing temperature. So you can tell what the bond type is based on the change in solubility. Those are a few things we can tell from this graph right now. Okay, here's another thing that we can do with graphs. We can also make some determinations of things that aren't written specifically on this graph. The first skill you could have is to extrapolate. So extrapolating means that even if something's not on a graph, you can make certain determinations. So for example, if somebody asks you something about the solubility of Ki at 50 degrees Celsius, you can say, well, 50 degrees Celsius is not on this graph. That doesn't mean that you can't tell anything about the solubility. What it means is you can make the determination that the solubility is going to keep increasing to a certain point, and that you can say that, well, I don't know exactly what the solubility is. I can't read exactly what the solubility is off of this graph, but I can tell you it's greater than 150 grams per 100 grams of water. So that's called extrapolating. Notice that the solubility of Ki is the greatest of all the salts on this chart. KNO3 has the greatest change in solubility of any of the solids on this chart. Who can find the line that has the least change in solubility on this chart? NaCl has the lowest change in solubility. So the solubility of NaCl remains fairly constant with changing temperature, which is a good thing for us because think about the changing ocean temperatures. You've got these Gulf streams that's taking warm water and moving it up along the East Coast. And as it moves up, the water cools. Can you imagine what would happen if the solubility of NaCl or salt was going to decrease with decreasing temperature? Then you would have a lot of salt depositing out. So eventually that would disrupt the balance. Here's another thing that you can read off of here that's not written directly on the graph. So that's extrapolation. You can also do interpolation, which means that you make some determinations about things that aren't written on the graph. And I'm going to show you another skill. So let's go back to our KNO3. The solubility of KNO3 at 60 degrees Celsius is 110 grams of KNO3 dissolves in 100 grams of water. This is how we write our ratio. They might ask you, even though it's not written on this graph, how much KNO3 would dissolve in 50 grams of water? This time we can use X in a ratio. So you'd multiply each side by 50 and you would solve for 55 grams of KNO3 would dissolve in 50 grams of water. So this is how we make a ratio. Everybody make sure you write that down. That's the strategy for making a ratio. You can also read stuff on here and make interpretations on it. Let's say you only had 80 grams of KNO3 dissolved in 100 grams of water here. They might ask you how much more will dissolve. Well, the answer is the difference between 110 and 80. We know when we say difference, we always mean subtract. They might ask you, if I tried to dissolve 140 grams of KNO3 at 60 degrees in 100 grams of water, how much would precipitate out? We're not talking about a supersaturated solution here because they don't mention a temperature change. So you would say 30 extra grams would precipitate out. Remember, a precipitate is a solid that settles to the bottom of a solution. So these are things that we can calculate or infer from a graph. One last thing that I want to make sure that you understand is that the whole metric system was built around water. That's why a nice and easy freezing point of 0 degrees Celsius, nice and easy boiling point of 100 degrees Celsius, and a nice and easy density. The density of water is 1 gram per milliliter. That means 100 grams of water is equal to 100 milliliters of water. A milliliter is also an example of how we made the metric system so easy for ourselves, because 1 milliliter or 100 milliliters is the same as 100 cubic centimeters. What that means is you can actually take measurements of length and turn them into volumes, which is unique to the metric system. You can do it in the English system, but it's super complicated. So I can tell you 1 centimeter cube, or a box that is a centimeter long on each side, contains 1 milliliter of liquid. If I had a box that was a cubic inch, I'd have to divide by 12 3 times. It would be very complicated. I also want to point out an old-fashioned abbreviation for centimeters cubed or milliliters is called cc's. So if you ever watch medical dramas, they might say, oh, he needs 100 cc's of blood. That stands for cubic centimeter or centimeter cubed. It's an abbreviation that allows you to not have to use superscripts. Another important one that I want you to remember is that 1 liter is also a derived unit. 1 liter is the same as 1 decimeter cubed. There's 10 centimeters per decimeter, so 10 times 10 times 10 is 1,000. And notice, if you remember, there's 1,000 milliliters in a liter. So if I had a cube that was measured 1 decimeter on each side, the volume of that cube would be 1 liter. So I can take measurements of length and change them into volumes, which is super easy in the metric system, super difficult any other way. So let's summarize the things that affect solubility. For gases, it is temperature, bond type, and there's one more we haven't talked about yet. And if you think of a 2-liter bottle of pop, you know when you open it, you hear that whoosh. That comes from pressure. Solids, pressure doesn't count for solids. But temperature, bond type, and the last one, you might have guessed based on what we've learned, is surface area. So these are the factors that affect solubility for gases, and these are the factors that affect solubility for solids. And there is a summary on how to read the solubility table that you were given today.